For our Aerospace 351 final design project, we designed an environmental control and life support system for a prolonged mission to Mars. We are Team 4, and our members are Ana Paula Pineda Bosque, Amy Comeau, Sean Thompson, Sam Albert, and Ricardo Gomez. For an ECLSS system such as this, there are several important stakeholders involved. There are investors, such as venture capital firms, suppliers, such as a company that makes CO2 filtration systems, the astronauts, such as some of our famous Purdue alumni, national and international space agencies, such as ESA or NASA, and commercial space companies like SpaceX or Blue Origin. For a mission as hazardous as a long-duration mission to Mars, there are a lot of risks to consider. A couple of example risks are a fire on board the spacecraft or bacterial growth in the filters. We listed all of the risks we could come up with, and then we rated each of them on their likelihood and severity. So for example, a fire has a low likelihood but a high severity, whereas bacterial growth has a medium likelihood but low severity. Once we've compiled all of the risks, we add them into this risk matrix, again ranked by their likelihood and their severity, and we can easily see which risks are most important to address right away. So for example, electrical failure, because it is highly severe and happens on occasion, is in the medium zone, which is colored orange. But because bacterial growth also happens on occasion but is not severe, it's in the green and is less severe of a risk to address right away. Now we're ready to begin our concept generation. After our initial research, we divided the ECLSS system into 4 key components. First, waste management system. Second, water processing. Third, air revitalization. And fourth, thermal control system. Next, we're ready to generate some concepts for each of these categories. We did this through 2 main techniques: brainstorming and research of prior technologies. We found several key prior technologies which we used in our design. Firstly, there were existing implementations, such as the waste management process on the shuttle program and the air purification system on the International Space Station, or ISS. There are also several solutions which have been proposed. For example, the Purdue Human Journey to Mars project or the CU Boulder Mars or Bust project. Now that we've generated several concepts, we need to perform some initial calculations to inform our design. Here's an example of one of them where we're calculating the amount of water we need to bring on our journey to Mars with us. So, we know that we have 6 crew members and that the journey to Mars will take about 9 months or 273 days. We also know that the average person will need to intake 1 gallon of water per day. Now, we can reclaim the water that's lost through sweat or urine, but not the water lost through solid waste. So, each crew member will lose about 0.024 gallons of water per day. The efficiency of our chosen water reclamation system, or the cascade distillation system, is about 90%. So, when we run through those calculations, we realize that we will lose a little more than 1/10 of a gallon per day per crew member of water. Then, if we add that up across the 9 months and multiply by a factor of safety of 1.5, then add on top of that the 12 gallons of water that we start with, we realize we should bring at least 310 gallons of water with us for our 9-month journey to Mars. For the next step in our design process, we ranked the benchmark technologies against each other using Pew decision matrices. And we did this for each of our 4 main categories, where the example here is for our air revitalization system. And we're ranking systems from the International Space Station, CU Boulder, and Paragon Space Development Corporation. And we rated each of them on our 4 main priorities: cost, mass, reliability, and efficiency. You can see that we don't actually have data for cost because we struggled to find reliable information on this for many of our systems, so we ranked mass, reliability, and efficiency on their relative weights. You can see that reliability was rated as at a 1 through 5, 5 being the most important. Once we calculated up the totals, ISS came out on top with a high score of 59. So for our final design, we took most into account this current solution on the International Space Station for air revitalization. After ranking our benchmark solutions in our decision matrices and choosing the best benchmark solution for each case, we now have a final system made up of the ideal components for each category. We have our waste management system, which collects and contains and finally disposes of hazardous waste. We have our water processing system, which recycles wastewater to be drinkable again. We have our air revitalization system, which keeps O2 levels and CO2 levels at healthy rates. And finally, we have our thermal control system, which keeps the astronauts and equipment at a happy temperature. Combining all of these 4 components, we now have our ideal ECLSS system. To conclude our video, let's go over a few things that we would do differently next time. First of all, it would be good to choose a project which is significantly smaller in scope. Choosing something so large was exciting, but made us unable to really dive into the detail level of a lot of the design. Secondly, it would be good to trust the process and know that writing our requirements will lead us to a final solution rather than having a final solution in mind while we're writing those requirements. Lastly, we learned that cost analysis is particularly difficult when you don't have existing solutions on the market. So again, scoping down our project would help in this area. Overall, we learned a lot from this project, and we hope that you've learned a little bit more about cutting-edge ECLSS systems. Thanks. Keep going.